Hi, welcome back to my channel. This is Pushpita here. In this session, let's discuss about the application of Euclid's division lemma. This lemma has several applications related to finding the properties of numbers. Let's do some examples. Question 1. Prove that any positive integer is of the form 3q or 3q plus 1 or 3q plus 2 for some integer q. We have learned that any positive integer is of the form a is equal to bq plus r. When we compare this with 3q or 3q plus 1 or 3q plus 2, we get b is equal to 3. Now, let us assume a positive integer a and b equals 3. Then, by Euclid's division lemma, we get a is equal to 3q plus r such that 0 less than or equal to r less than 3. Now, the possible remainders are 0, 1 and 2. When r equals 0, we get a is equal to 3q. When r is equal to 1, a becomes 3q plus 1. Also, when r equals 2, we get a is equal to 3q plus 2. Hence, any positive integer is of the form 3q or 3q plus 1 or 3q plus 2 for some integer q. Let's see the next question. Prove that one of every 3 consecutive positive integers is divisible by 3 for any positive integer n. To prove this, let us take 3 consecutive integers n, n plus 1 and n plus 2. We know that any positive integer is of the form 3q or 3q plus 1 or 3q plus 2 as proved in the previous question. So, applying this, when n is equal to 3q, the consecutive numbers becomes 3q or 3q plus 1 or 3q plus 2. Among this, only n is equal to 3q is divisible by 3. When n is equal to 3q plus 1, we get the numbers 3q plus 1 or 3q plus 2 or 3q plus 3. In this, only n plus 2 is equal to 3q plus 3 is divisible by 3. When n is equal to 3q plus 2, here we get 3q plus 2 or 3q plus 3 or 3q plus 4. In this, n plus 1 is equal to 3q plus 3 is divisible by 3. Therefore, in each case, only 1 is divisible by 3. Hence, one of every 3 consecutive integers is divisible by 3 for positive integer n. Let's do the next question. Use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. In this question, we have to prove that the square of a positive integer is either of the form 3m or 3m plus 1. In order to apply Euclid's lemma, consider a variable other than m which is given in the question. Let us take q to write this lemma. Now, let us assume a positive integer a and b is equal to 3. Then, by Euclid's lemma, we get a is equal to 3q plus r such that 0 less than or equal to r less than 3. Now, the possible remainders are 0, 1 and 2. When r equals 0, we get a is equal to 3q. Squaring both sides, we get a square is equal to 3q the whole square, that is equal to 9q square. It can be written as 3 into 3q square, that is equal to 3m, where m is equal to 3q square. When r is equal to 1, we get a is equal to 3q plus 1. Squaring both sides, we get a square is equal to 3q plus 1 the whole square. Expand 3q plus 1 the whole square using the identity a plus b the whole square is equal to a square plus 2ab plus b square. We get a square is equal to 9q square plus 6q plus 1. Taking 3 from the first two terms, we get 3 into 3q square plus 2q plus 1. This is of the form 3m plus 1, where m is equal to 3q square plus 2q. Now, take r is equal to 2. Then a is equal to 3q plus 2. Squaring both sides, we get a square is equal to 3q plus 2 the whole square. That is, a square is equal to 9q square plus 12q plus 4. We have to write this as 3m or 3m plus 1. Is it possible? Yes. 4 can be written as 3 plus 1. Then we get a square is equal to 9q square plus 12q plus 3 plus 1. Taking 3 from the first three terms, we get a square is equal to 3 into 3q square plus 4q plus 1 plus 1. It is of the form 3m plus 1, where m is equal to 3q square plus 4q plus 1. Hence, the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Let's discuss the next question. Question 4. Use Euclid's division lemma to show that the cube of any positive integer is of the form 9m or 9m plus 1 or 9m plus 8 for some integer m. It is similar to the previous one. Here, the divisor given is 9, but 9 is a multiple of 3. So, instead of 9, we can take 3 for applying lemma. Let a be any positive integer and b is equal to 3. Then, by Euclid's division lemma, we get a is equal to 3q plus r, where 0 less than or equal to r less than 3. Now, the possible remainders are 0, 1 or 2. When r equals 0, we get a is equal to 3q. Cubing both sides, we get a cube equals 3q the whole cube. That is equal to 27q cube. This can be written as 9 into 3 cube, that is equal to 9m, where m is equal to 3q cube. When r is equal to 1, we get a is equal to 3q plus 1. Cubing both sides, we get a cube is equal to 3q plus 1 the whole cube. Using the identity a plus b the whole cube equals a cube plus 3a square b plus 3ab square plus b cube, we get a cube equals 27q cube plus 27q square plus 9q plus 1. Taking 9 from the first three terms, we get a cube equals 9 into 3 cube plus 3q square plus q plus 1, which is equal to 9m plus 1, where m is equal to 3q cube plus 3q square plus q. Again, when r equals 2, we get a is equal to 3q plus 2. Cubing both sides, we get a cube equals 3q plus 2 the whole cube. Applying the identity, we get a cube equals 27q cube plus 54q square plus 36q plus 8. Taking 9 from the first three terms, we get a cube equals 9 into 3 cube plus 6 q square plus 4q plus 8, that is 9m plus 8, where m equals 3q cube plus 6q square plus 4q. Hence we can conclude that the cube of any positive integer is of the form 9m or 9m plus 1 or 9m plus 8 for some integer m. Stay tuned. We'll meet in my next video. Thank you.